Hi, everybody, and welcome to Slooh.com. I'm Jeff Fox. I'm joined by our Slooh astronomer, Bob Berman, tonight. And the reason that we're on this evening is because we are going to bring you live from Australia the annular solar eclipse of the 29th of April, 2014. One of those things where, depending on where you are in the world, it may still be the 28th, but in the Eastern Hemisphere, in Australia and Antarctica, this is happening in the late afternoon and the evening. We have a live feed that we're going to be bringing you from Newcastle in Australia, which is on the southeastern coast, which is courtesy, by the way, of our Slooh telescope partner, Gerard Lazarus, and we very much appreciate his feed. It's an interesting eclipse to a great extent for what it isn't. And to join me and talk a little bit about that, let's bring in Bob Berman. And Bob, I mentioned to you a little bit earlier before we went on, this just barely qualifies as an eclipse.
Well, that's right. You know, in the pantheon of eclipses, probably the highest and the mightiest and the one that brings tears to people's eyes and makes animals go crazy is a total eclipse of the sun, a total eclipse. But people rarely see them because for any given spot on Earth, one happens only once every 360 years. And then if it's cloudy, you have to wait another 360 years. So you almost always have to travel, and they only occur over a very narrow band of Earth. Second, probably in terms of spectacularness, is probably a toss-up between a total lunar eclipse. We're having two this year. Slooh is bringing both of them to us. Of course, one was just a mere week and a half ago, and the other is going to come up on October 8th of this year. Very rare for the United States and Canada to have two total lunar eclipses in a year. And then maybe tied with that is an annular eclipse, and that's what we've got today.
That is what we have today. And let's talk about that in just a minute. Before we go on, let me tell the folks who are joining us tonight who may not be familiar with us a little bit about Slooh. Slooh, SLOOH.com, is a community telescope organization. Our members have access to some fine telescopes with our site located in the Canary Islands and also our new, or actually, we have a community of people who love astronomy, who love looking at the sky. And so they have access not only to the imagery that our telescopes can get, but also our members have the opportunity to schedule time slots and actually point these telescopes and look at the nighttime sky from just some amazing locations with really fine equipment. We'll talk more about that as we go on. Let's talk more about the eclipse tonight, Bob. What we're talking about here is an annular eclipse. That's where the moon does not totally cover the sun.
That's right. It means it's gliding centrally over the sun if you happen to be in the right location. And I know we're going to talk about that because this is the most unusual annular eclipse of my life and yours. And we'll get to that in a minute. But the whole idea is that the moon glides centrally over the sun, but is too far away because the moon has an oval orbit around Earth, so it's carried closer and farther away, and only when the moon is in the nearer half of the orbit does it appear large enough to precisely match the sun in size in the sky and completely block it out. If it looks too small, if it's in the farther half of the orbit, which is where it is right now, then it will leave behind, even when it's centrally over the sun, a ring or annulus of sunlight. Annular sounds like it's once a year, but here annular means ring-like and leaves behind a ring of fire around it.
And I believe that we have actually an image of what we would expect that the sun would look like. Michael, if you can find that for us, That is the ring around the moon that we looked at a little bit earlier. Yeah, that's the one. And this is what it will be looking like in the area where it is an annular eclipse. It's that little inset box that you see the lower left-hand side of your screen. Bob, the area where this can be seen is really small, isn't it?
Never seen anything like that because really this eclipse is missing planet Earth largely. It's flying out into space just south of Antarctica so that the people who are stationed there at the South Polar Research Station, if they could crane their necks like Rubber Man and raise their necks up hundreds of miles into space, well, so the sun would strike them, and so would the moon blocking out the sun. Then they would see a nice central annular eclipse. But they can't because there is no sun shining there. The sun set for keeps about a month ago. So they're in their 6 month long Antarctic winter. So you'd have to journey hundreds of miles, many hundreds of miles from the South Pole until you get to the place where the sun is just barely up, just over the horizon, to now be in a position where you see the moon blocking out the sun, leaving a ring or annulus of sunlight. And so that winds up being a little tiny spot, uninhabited by anyone except penguins. I'm not even sure penguins are there.
I don't even think penguins are
They're,
there.
they're calling this the penguin eclipse, but penguins live in Antarctica. But I don't think I'm no expert, of course, but I don't think they go inland that far. So this is an area that no human being will be able to see it, and we've never had this before. Never an annular eclipse that just simply is not accessible to anyone. So
And
that's weird.
actually, the area that the annular eclipse will be seen is D-shaped, and this goes back to part of what you said before. The reason that it's D-shaped is the straight edge portion of the D is actually the sunset line.
Yes.
So the places where it will be seen as an annular eclipse, and that would include this very small area in Antarctica, it'll be happening when the sun is literally on the horizon getting ready to set.
Right, which actually would look pretty cool to see that. It would look very amazing to see an on the horizon sun that's not a sun at all, but a ring of fire. Because when the sun is so low, as we all know, its light has diminished enough to look at it without eye protection. We've all looked at sunsets when the sun is right on the horizon. We've looked at that safely. So if you were there, you would not need the solar filters that you normally need to protect your eyes during an annular
Ah.
event.
And when we see it coming through from our camera, which is what you're seeing on your screen now, from Newcastle in Australia, we're only going to see a partial eclipse. This will be, I believe, around 60% at its maximum. And you said, really, this is not very noticeable, even to people who would be on the ground where it was happening.
Right. If you didn't know it was happening, you might notice a slight diminution in sunlight, the kind that would happen if there's a little bit of a cloud partially obscuring the sun, not completely obscuring the sun. You really have to know it was happening and then use eye protection. In the old days, they used smoked glass, not smoked grass, smoked glass. They used puddles of water because a reflection from a puddle of water diminishes the light somewhat. These are not all completely safe methods. These days, we like to use shade number 12 or 14 welder's goggles as ideal solar equipment. And then with that, you'll see a deep partial eclipse where the sun will be reduced to a lunar-like crescent. So that's pretty cool. And that's what we will see tonight.
Yeah, and as you can see, the solar disk is available, and is visible, I should say, from our location in Newcastle, Australia. I heard earlier that folks who wanted to watch from Tasmania, which would be farther to the southeast, just south of the main body of Australia, they've been weathered out tonight. So for many people, even in the areas, and how often has this happened, Bob? In the areas where you should be able to see at least something, are being weathered out of this event.
Right, exactly. So this will be seen from Australia, all parts of Australia, including a little bit to the west of Australia where they're searching for that Malaysia airliner ship. So just to give people an idea of what's in the news, where this thing is, and how remote it is, to be able to see it. So we're getting ready to watch the moon start to block out the sun.
Let's talk a little bit about Slooh for those of you joining us tonight and hearing about our coverage. What we're going to be showing you is a live video, live from Australia, from our partner, Gerard Lazarus. This is a specially filtered image that you're looking at. So you will be able to see the sun. You will be able to see as much as the lunar disk covers the sun as it goes through without the normal glare that we would have if you try to take a picture or, heaven forbid, look at it yourself. And the reason that Slooh is involved is we're a community of people who are very interested in astronomy. The Slooh community is involved in many, many projects, not the least of which is tracking asteroids and tracking comets. Much of that being done by our Slooh telescopes, our two robotically controlled scopes in the Canary Islands, and then the robotically controlled scope in Chile. A little bit later, we'll be showing you some of the images that some of the Slooh members have been looking at over the past few nights. These are really fine observational telescopes located in just great locations. Our location in the Canary Islands is almost or over, I should say, 7,700 feet above sea level, meaning to a large extent it's above the weather. It's located in one of the finest locations in the world for observing, where the laws have a sensitivity to light, so that people or businesses in the Canary Islands coexist nicely with telescopes like ours. We have a half-meter telescope and also a 35/100ths meter f11 Schmidt-Cassegrain telescope there. And like I said, Bob, a little bit later we'll show some of the images that our Slooh members are looking at or have looked at over the course of this week. And for those of you who are interested, by the way, before I get back to Bob, the Slooh.com website has a lot more information. And if you find that this is something that interests you, we are having an introductory membership offer that's going on right now. So you can sort of dip your toes in the pool if you want. That's 3 months of Slooh membership for $29.95, also known to us as $30. You'll save 60% over the normal price. And it's a way to find out if Slooh is for you, and to find yourself with our Slooh community of observers. And I think to a great extent, that may be our most powerful thing that Slooh provides, because there are other people who have similar likes to yours, who want to know about what is going on in the sky, who are looking at those quirks and little things that come from time to time, those small events like comets and asteroids. And there are lots of people online within our community who want to spread the word, who want to proselytize what they do. So is help available if you're starting out? The answer is yes. Bob, before we talk, I understand that we have Dr. Lucie Green standing by, and if it's okay, let's bring her in.
Oh, excellent. Lucie's great. Let's do
Lucie, good evening. I'm Jeff Fox. How are you this morning, or I guess this evening where you are? Oh, all right. She's not yet. All right. Well, then we'll get back to her in just a moment. Bob, so let's talk about let's talk a little bit more about this eclipse and other eclipses that are coming up. From a scientific standpoint, I heard all sorts of discussions about how lots of research can be done during total eclipses. Unfortunately, you lose a lot of that when you have an annular eclipse, right?
That's right. Annular or partial or lunar eclipses, whether partial or total. The real science comes from total solar eclipses. Alas, they are so rare. We'll next have one on March 20th next year, 2015, and then there will be one on 2016. We get one 3 out of 4 years. That's the good news. Bad news is that they almost have a phobic fear, the moon shadow does, of convenient places, and so the shadow tends to fall in near the North Pole or really crazy places. On March 9th of 2016, it'll be over the steamy, overcast jungles of near Sumatra and Borneo. Although there will be a cruise ship heading towards north of Hawaii, and we'll be seeing it from there. Then we finally have one in the United States coming up on the 21st of August, 2017. We've waited 38 years, been a long hiatus, 38-year drought of no total eclipses over the mainland United States. That's finally going to break in the year 2017.
And for those of you just joining us, what you're looking at is a live picture from Australia from our Slooh feed partner, Gerard Lazarus. You're looking at a filtered picture of the sun. It is afternoon in Australia right now, and the path of this annular eclipse is moving from the area around the Antarctic continent. I want to say around the South Pole, but the truth is, this eclipse actually will not be seen at the South Pole because it'll be after sunset there, and sunset. A slightly different concept at the North Pole. Sunset wasn't today or yesterday. Sunset happened last month, right?
That's right. It happened on March 20th, although thanks to the refraction of the atmosphere, it actually delayed that a couple of days. But let us say by March 24th, the sun was gone for keeps, and that's going to last for 6 months.
And in a place that is inhospitable and remote and difficult to get to and stay in. This is in the area of annularity, the area where the moon will block out as much of the sun as it does in this eclipse, is in an incredibly remote spot located basically south of southwestern Australia, in as about an inhospitable place as you can get. It's likely, Bob, that no one will see this live, though I wouldn't be surprised after the fact if we start seeing some imagery come back from some of our observing satellites, which may be in a good position to actually see this. Though, is that cheating when you're off the surface of the Earth to see an eclipse?
Yeah, that's cheating because we're deprived of it. But yes, maximum eclipse is going to happen at latitude south 70 degrees, 70 degrees. So it'll be a full 20 degrees of latitude from the South Polar Station itself, unfortunately. So that means since each degree of latitude is almost 70 miles, so you're talking about 1,400 miles you'd have to venture from the research station to get to the spot where you could see the ring of fire. So what we're going to see in Australia, in eastern Australia, is a deep partial eclipse.
Okay, and Michael, you tell me, do we have Dr. Green with us? We do. Okay, and we're joined by Lucie Green. Good afternoon. It's my understanding that we have you this afternoon from Japan. Is that right?
Good afternoon. Yes, I'm in Japan. I'm actually en route to Australia, but I won't make it in there in time for the eclipse.
Okay. Well, the reason that we want to talk to you is because we're looking so much at the sun this afternoon, and the sun is your specialty. Not looking at it with the naked eye, but looking at it and thinking about it from a physics standpoint. And there's a lot that we have been learning about the sun over the past few years, things that we never knew, right?
That's right. Studying the sun at the moment is a very, very lively research topic. I mean, it has been for many decades now. And my particular area of interest is watching the sun from space, actually using satellites, and that means we can see the sun in all kinds of ways that we can't do from the ground, because we can use wavelengths of light that don't penetrate through our atmosphere, like ultraviolet light and X-rays. And I think probably one of the big questions in solar physics at the moment is what's driving the solar cycle, what's causing the variation in these dark features that we call sunspots on the surface of the sun. Why do their numbers ebb and flow?
This is the normal 11-year solar cycle where we go through a minimum and maximum of sunspots?
That's right. So there are times when there are very few sunspots on the surface at solar minimum, and then the number ramps up over 5 or 6 years to maximum and then fades away again, only for the whole process to start all over again. And it goes on and on and on. And we've been watching it with telescopes now, well, ever since the early 1600s, and before that with naked eye observations from countries like China.
Yeah, I just want to point everybody, while we're talking, Lucie, to our photo, to our live feed from Australia. And if you look down in the lower right-hand portion of the disc, Bob, correct me if I'm wrong, I believe we're starting to see the beginning of the moon crossing portions of the sun. This from our observatory in Australia.
Absolutely. It's underway.
So, Lucie, there are a number of things. Allow me to be a fool and ask you some simple questions, if that's okay.
Oh, that's fine.
Okay. Well, now, it's my understanding that the surface of the sun is actually not as hot as the outer reaches of the sun. That makes no sense to me. Can you explain it like I'm 5 years old?
It is a real puzzle, and it shocked people when they found out. So the surface of the sun that we can see in the live feed that's coming from Australia has a temperature of around 6,000 Kelvin or 6,000 Celsius. It's sort of the same when you're up at those figures. And that's something we could work out just by looking at the light coming from the surface of the sun. But then observations started to show that there was this atmosphere mostly invisible to us, except for these times of a total solar eclipse when suddenly you see this halo around the sun. So it's not something that we'll see with this eclipse, because it's not a total, it's an annular eclipse at the greatest eclipse point. But total eclipse observations showed the sun has this atmosphere. And then as observations progressed, and in particular when we got satellites above the Earth's atmosphere and we studied the atmosphere from space, people realized that the atmosphere had a temperature of millions of degrees. And that's just completely counterintuitive. How could you possibly have a hot atmosphere overlying a relatively cool surface? It begs the question, what is heating that atmosphere?
And what is?
Well, we think that we are really coming on in our understanding of that, of answering that question. And it looks like it comes down to the fact that the sun is not only a sphere of very, very hot gas, or an electrically charged gas that we call a plasma, but it also has a magnetic field. And that magnetic field could act as a sort of tube to channel heat from the solar surface, or channel energy really from the surface that we're seeing now up into the sun's atmosphere. So magnetic fields can store energy, they can release it, they can guide energy, and there are lots and lots of ways that energy could be transported from the solar surface up into the atmosphere. So I think we sort of understand the broad base, the broad description of it, but all the details are still being worked out.
The sun obviously is what brings us heat and light here on Earth, but the sun is also a very active star, at least for us it is, considering how close it is. It's something we should look at. How active, talk to me a little bit about what's going on at any moment on the surface of the sun.
The sun is always so active and always so interesting. And a lot of it comes down to the fact that it has a magnetic field. And there's a quote that sometimes gets talked about in the solar physics community. And I don't know who first said this, but the quote is basically that the sun would be a very boring star if it wasn't for the fact that it has a magnetic field, because otherwise it would be this bland sphere of gas. But the magnetic field, and like I said, it introduces, or it stores energy, and when that energy is released, it can power very, very dramatic events. So yeah, it's a good question to think about. What could the sun be doing, or what is it doing as we're looking at it now? Well, the layer that we're seeing through the live feed from Australia, that will be the gas there will be in turmoil, and it will be moving and it will be churning because the sun is hot. So hot gas is rising and cool gas is sinking. It's happening in the room around me now as I've got the heating on, and it's also happening in the sun. And those motions move and churn up also the magnetic fields. And that can cause very, very energetic events that we refer to as solar flares. So these are huge explosions that happen in the sun's atmosphere, and they release a lot of energy, and they make the gas in the atmosphere shine very strongly in X-rays, ultraviolet light, but also in radio waves. They can make the surface shine very brightly in different wavelengths too.
And they can also even induce currents because of the I guess the magnetic force that's thrown off. Haven't there been times when power grids have been shut down because of solar storms passing through the Earth's magnetic field and inducing currents in electrical transformers and the like?
There have. So the other component of a solar flare, or something that can happen at the same time and is related to a solar flare, is actually what I study, and it's an eruption from the sun's atmosphere that has a very unusual name. We call them coronal mass ejections. It's not really a phrase that rolls off the tongue, but it sort of does what it says on the tin. So coronal, which refers to the corona, the atmosphere of the sun; mass, it's referring to material; and ejection, this material is being ejected from the sun's corona. But it also carries with it the sun's magnetic field. So the sun is this electrically charged and magnetized object, and sometimes portions of this atmosphere, which has electric currents flowing through it and magnetic fields, erupts into space. And it's when those magnetic bubbles slam into the Earth's own magnetic field that it can become distorted. And it's a very complex series of events that happens, but really the end point is that changes in the Earth's magnetic field propagate down. They come down through the Earth's magnetic field, they come down through the atmosphere, and they can create currents where our feet are, at ground level. And if electric currents are created, where do they flow? Well, they might flow through rocks, but they could start to flow through our electricity networks. And when those currents flow, they can interfere with the networks and cause problems. And in the most extreme case, you could have failure of transformers, which then could bring parts of the power grids down. So the famous example is one that happened in Canada in 1989, when we had very high levels of activity from the sun and lots of coronal mass ejections came our way. So, the sun is beautiful to look at, but it really does have a day-to-day impact on our lives.
And it actually also, I understand, affects satellites because it can change the shape of our atmosphere and so create additional friction for Earth orbiting satellites.
That's right. When the solar flares go off, they send out lots of energy in the form of radiation, so light across different wavelengths, out into the solar system. And when that light reaches the Earth's atmosphere, it heats it up and it starts to expand. And our satellites find themselves in denser regions of the atmosphere as it expands up over the spacecraft. And then, as you say, they experience more drag, they start to move more slowly, and then they could literally fall out of the sky. They could come spiraling in if there aren't corrections made. And there are cases where satellites have, in fact, solar physics satellites have been affected by high levels of solar activity. So one of the biggest ones is Skylab, which was the American space station, which had on board a fleet of solar telescopes. And that was brought down early because of high levels of solar activity. So we have to watch out for what the sun gets up to.
All right. I'm Jeff Fox, and I'm joined by our Slooh astronomer, Bob Berman. And you've been listening to Dr. Lucie Green, who's the solar scientist at the Mullard Space Science Laboratory of the University College in London. And what you are looking at now is live images coming to us from Australia. That is where a partial solar eclipse will be, or not will be, is actually occurring. What you're looking at now is a portion of the moon, which is blocking out the afternoon sun. This image that you're seeing is coming to us from Newcastle, Australia, from our Slooh feed partner, Gerard Lazarus. Lucie, if I may ask, is there still solar science to be found by making observations during total eclipses?
There's a lot of science that still can be done. I mean, it changes and evolves over the years, but certainly one really strong benefit of studying the sun from the ground during a total solar eclipse is that we can take a series of very rapid images. So if you sort of think at the other end of the spectrum, if we're using satellites in space, once the satellite is launched, that technology can't be changed. And because we have to build things so robustly, the technology is quite often a few years behind what we have down on the ground. So, for example, the amount of data that we can store on our satellites isn't as much as we can store down on the ground, and it is hard to send a lot of data back as well. So if we want to take lots and lots of images, very rapid fire images of the sun, we can do that from the ground during a total solar eclipse when we can see the sun's atmosphere revealed. And that's really useful for looking for those mechanisms which heat the atmosphere actually. So what is it that's channeling energy from the solar surface into the atmosphere? So for example, it could be waves. And these waves have very rapid oscillation, so you need very, very quick sequence of images to see them. And I think for me, that's where the strength of observing a total solar eclipse from the ground really comes in.
All right, let me just switch directions for just a second. If you can stand by, Lucie, let me bring Bob Berman back in. Bob, for those who are watching us tonight, or during the day, depending on where in the world you are, let's get everybody set up with exactly what they're looking at on the screen right now.
Well, where you're looking at the sun from Australia, you can see some evil entity is taking a bite out of it. Well, that's what we might have said a couple of thousand years ago. Instead, here's proof that it's really circles up there. The sun is a giant sphere, 865,000 miles across. The moon is a sphere only 2,160 miles across. So why does the moon happen to just arc of the black sun's of the moon's perimeter as it's biting into the sun? You can see those arcs are the same size, so they're both the same size disks. That's because of the amazing coincidence that while the sun is 400 times larger than the moon, it's also 400 times farther away. And that allows, and it didn't have to be that way. It's true.
No, I was just going to say, Bob, as far as I know, I can think of no other planet in our solar system that has a moon that matches up this way with the sun.
Quite right. For example, it's famous that the moons of Jupiter, the giant Galilean satellites, cast shadows on Jupiter's cloud tops. But if you were there, those moons appear larger than the sun appears from Jupiter. So they would more than block out the sun. The sun would appear as a smaller disk than each of their satellites do here only on Earth. And only during the current time, because the moon is spiraling away from us. It's going away. It's leaving us at the rate of about 2.5 inches a year as it gets farther and farther away. So in some millions of years from now, the moon will appear too small to fully cover the sun. And then every eclipse, central eclipse, will be an annular eclipse, as today's is.
Well, let me welcome everybody who's watching us today. You are watching Slooh.com, and we are covering the annular lunar eclipse. The only place of annularity, that would be where the moon does not quite entirely cover the solar disk, was a very small section of Antarctica, a place so remote that we assume that no one saw this live. What you're looking at now is part of a partial eclipse. Partial eclipse being seen all across the Australian continent late this afternoon for them. This image that you're seeing is coming to us from our that's located in southeastern Australia, near not very far from the coast. And as you can see, we have a very good view of the moon coming across and blocking out the sun. Lucie, we've been talking about the sun a lot, and really this is sort of happenstance, isn't it? Because as far as the sun is concerned, eclipses are not part of its business. This is something that only we see from Earth. There's no effect to the sun at all, right?
No effect at all. So absolutely no changes on the sun will happen because of this. The moon is just going about its business in orbit around the earth as it always does. The only thing that would cause any changes within the sun and the moon system would be a change of mass and then a change of the gravitational attraction between them, but that's not happening. So yep, it's just normal day-to-day business for the sun.
Lucie, if somehow we had the ability to go to the sun, is there a solid surface at all? Is it all a gaseous giant? What would the surface, or is there a surface? What would it be?
Do you know, it would be very, very challenging. So we've talked about the heat already, but as you asked, there is no solid surface to the sun. So even if we could withstand the heat, we wouldn't have a surface to land on. And I do find it incredible that the view we have of the sun, so what the layer we're looking at now is often called the surface. Really, its technical name is the photosphere, which means the sphere of light. So this is where the visible light is being emitted from the sun. And we call it the surface, but it sort of looks like a surface. It looks like a well-defined surface. It has a very sharp edge, as you might expect a solid surface to have, but it's not. It's still a gas. So if we were ever able to get to the photosphere, spacecraft that you'd need to be in, but it just so happens that within a layer of about 500 kilometers, which is not very much over the whole radius or the whole diameter of the sun, but across that very narrow layer, that's where the sun emits visible light. And so it looks like this very well-defined thin layer and gives the sun a very sharp edge. If it wasn't a well-defined layer, the sun would look like a sort of nebulous, fuzzy object in the night sky, perhaps more like the red giant Betelgeuse looks. If you've ever seen any of the amazing images of that star, this red giant that's in the constellation of Orion, which is so large that we can just about make out its size and just about resolve it in our telescopes. And Betelgeuse looks slightly different at different wavelengths, depending on what color of light you use to look at it. But our sun has this very nicely and clearly defined edge, but it's not a solid surface.
Let's talk about one thing you just said here that I think some people may be confused by. You look at the sun with a telescope. You know, people think of telescopes to multiply the light, to bring in those lone photons from stars coming across the universe. The sun seems to be an unlikely target to use a telescope. So tell me how you're able to do that.
That's right. So with the sun, it's sort of the opposite to all the other stars, isn't it? As you say, with other stars, you're trying desperately to get as many photons, many particles of light as possible. But with the sun being so close to us, that is not a problem at all. And quite often we're trying to keep light out of our telescopes. So the reason that we use telescopes to look at the sun, I guess, is twofold. One is that we want to be able to zoom in. We want to be able to magnify and see the details on the sun. And the other is that we want to be able to select out different wavelengths of light. So at the moment, we're looking at what we'd call white light, which is all the colors of the rainbow. But sometimes we want to select out particular colors and study the sun only using those colors of light. And if there's any amateur astronomers watching the broadcast now, they may well own a filter called a hydrogen alpha filter, which selects out only a very particular color of light. And when you look at the sun in that way, you don't see a sort of featureless surface as the photosphere appears. You see the lower layer of the sun's atmosphere called the chromosphere, which has a huge amount of detail. You can still see the dark sunspots, but you also see long snaking black features that we call filaments, or maybe clouds of gas suspended above the edge of the sun that we call prominences. So telescopes they sort of extend our vision and give us bigger eyes to be able to see the details in the surface of the sun. So here we're looking at some images that show the lower atmosphere of the sun, and you can see it's much more structured now The edge is a little bit more fuzzy, but you can see there are long features on in the lower atmosphere, and to the top right of the sun, you can see some clouds of gas that are held up in the sun's atmosphere. So this view that we get through telescopes, I mean, it literally opens our eyes to what kind of star the sun is.
And once again, we're going back to our live feed from Australia. Before we go through this and talk more with you, Lucie, and with Bob Berman, Michael, can we put back up the image just to show how low in the sky this is in Australia? Because obviously our telescope is pointing or our observatory, I should say, is pointing and looking at the sun. But this is happening late afternoon in Australia. It's spring in the northern hemisphere, but in the southern hemisphere, it's now fall. So this is a late fall afternoon, and the sun, as you can see from this image on the screen right now, is pretty low in the sky. In fact, in many places, the controlling point on how long this eclipse will be visible at all is the fact that the sun will set even before the eclipse would actually be over if the sun would stay above the horizon. It's quite a complex dance going on because obviously the Earth is moving around the sun and the moon is moving around the Earth, and all of this is happening simultaneously as all of us fly through the universe tonight. So all of these things are coordinated in order to bring the moon in this particular position where it is right now. Bob, I think that we are looking now pretty much at about the maximum amount of coverage that we're going to see from Australia tonight. And this has not been, as you said, this is not exactly the greatest eclipse of our lifetime.
No, but I think it will progress somewhat more, Jeff. We're going to see a little bit more of the sun covered, and when we do, as we do, I'd like to bring up a point or two with Lucie, if
Sure,
I
please.
may. Lucie said something very interesting about that the visible light is emitted in only a 500-mile wide or thick region of the sun. And I wanted to ask her, is this because beyond 500 miles it becomes opaque, or is it because more than 500 miles deep visible light is not being emitted, which I don't think would be the case? Well, which would be the case there?
So it's a bit of both. So there's above the layer, well, below the layer, let's start below the layer. So below that 500 kilometer layer, the gas doesn't allow the light to pass through very easily at all. So it can only travel a very short distance before it starts interacting with the gas, the particles of the gas itself, and then the light gets stopped. But in this very special layer of the photosphere, suddenly as you say, the opacity, the ability of the light to pass through the gas changes drastically. And that's related to the fact that the gas changes in temperature, changes in density, and the particles that make up the gas stop interacting with it, and the light can stream through. But as you say, what's emitting the light? And it is the particles of the sun itself that gives off the light. In the photosphere, the electrically charged gas is giving off the light, but it can pass through and it streams out into space.
Okay, and then another issue, and I was just discussing this with Debbie Elmgreen, who just finished her term as the AAS president here in the United States. Here's an interesting point. You'll like this. You'll really like this. In the center of the sun, some have said that it would be pitch black because the sun's emissions in its core are essentially gamma rays and X-rays. And of course, it's very dense, so that paradoxically, the center of the sun would be pitch black. But I would think that there'd be some visible light being emitted even there, even in that flux of mostly X-rays and gamma rays. What would you think?
Yeah, what a wonderful way to think about the center of the sun and the birth of sunlight. That's where it's created. So the birth of sunlight is darkness because it's gamma rays that our eyes can't pick up, and therefore we don't define it as light.
Now, do you think there'd be some visible light though, even in the flux of mostly gamma rays and X-rays, or would it be solely gamma rays and X-rays, so that the center of the sun would indeed be pitch black to our
I,
eyes,
I
which is a wonderful idea.
Yeah, I think it would be pitch black. I'm trying to visualize in my mind, because it's not that only a very particular wavelength or color of light, very, very narrow one is emitted. But the frequencies or the colors of light depends on the temperature of the gas. And in the center of the sun, it's incredibly hot, 15 million degrees in the center. So, that dwarfs the few million in the sun's atmosphere that we were astonished by earlier. And I think that it would be pitch black in the center of the sun. I think that gas is too hot to be shining in visible light.
Well,
I think,
by
the way,
I like that idea so much, Lucy, that next time I write an article about it, I'm going to ignore Debbie's speculations that there would be visible light, and I'll preferably use yours. You're the solar expert after all, because the image is so delicious.
It is. I'm sort of thinking on my feet here, because I've not run the equation through my head quickly enough. But I think it would be pitch black.
All right, let me set this up for those who are joining us. A little bit of cloud cover has snuck in right now in Newcastle, Australia, which is where these live images are coming to us from. You are watching Slooh, Slooh.com, and if you've been listening to this conversation between Dr. Lucie Green of the Mullard Space Science Laboratory at the University of College London and of Bob Berman, our Slooh astronomer, then this is the kind of thing that interests you. Slooh is a community dedicated to astronomy. We are built around a number of robotic telescopes, two of which are located in the Canary Islands, one of which is located in Chile. These are available to our members to schedule and point to any object in the nighttime sky. The way Slooh's community works is that any one of our members can take a look at any of the images that we are that we obtain. So if one of our Slooh members schedules an observing session and takes a photo of something, it's available to all our members, not only to look at, but also to discuss. And that is a very valuable part of our Slooh community. Our website explains so much of what's going on, but I also want to let you know that we have an introductory membership offer, and this is a great idea. For a lot of people, having a really fine telescope at a fine location, as we do, is sort of a pipe dream. They're expensive. The locations are difficult to get to. Now with Slooh, you can have access to these telescopes, one now, or two, I should say, in the Canary Islands, one about to come back online in Chile, and of course, be a member of our Slooh community, which means lots of help, lots of how-tos, lots of hand-holding, and lots of people who share your interest and your passion. We have a membership special that's on right now. As I said, if you'd like to dip your toe in the water and see if this is something for you, you can sign up for 3 months for $29.95, which is a savings of 60%. And you can find out more about that by going to our website, which is at slooh.com. Let me spell it for you, because that's SLOOH.com. As you can see from the picture on the screen right now, we have been clouded out in Australia. This is always a problem, always something that you can be scared of when an event like this comes. Eclipses wait for no one, including clouds. So we are clouded out right now. But what we have been watching has been the partial portion of this annular eclipse. For those of you just joining us, an annular eclipse is an eclipse where the moon is reasonably close to the Earth. And so the size of the lunar disk to us is slightly smaller than the size of the solar disk. So instead of seeing the sun totally blotted out as you would in a full eclipse, what you see is a ring. And Michael, if you have just a second, we can show everybody what we feel that this probably looked like a little bit earlier this evening. The only place that this could be seen was an extremely small area of the Antarctic continent, a place that is so remote and so inhospitable that we don't think that anyone was there to watch it. Bob, if you look at this picture, and I'm going to ask you because I think this is more your expertise than Lucie's. I noticed that in this simulation that we're looking at, and that's what this is, a projection, it is not linear. There is a little bit more of the moon covering the upper fringes of the sun than the lower. This is because of the lunar orbit, which is off the plane of the Earth's orbit around the sun, right?
Yes, but that's not the reason that we're seeing this asymmetry in the ring. It's because the exact center line of the eclipse misses planet Earth entirely and misses it to the south of the South Pole. So you'd have to actually be in space to see an even ring on the in the path of annularity such that it hits Earth in that little section of Antarctica. It's off center. That's why you get this asymmetry here in the ring, not a perfect ring.
But you're going to have to take our word for it because, as I said, this part of it is pretty much not visible to anyone. What we have been looking at and what has been clouded over within the last few minutes has been an observatory located in southeastern Australia, in Newcastle, Australia. And the weather there had been great for most of the afternoon. We know that the eclipse had been weathered out in Tasmania down to the south of Australia. But right now, we'll go back to the live view. You can see there are some clouds, and that's now making it pretty difficult to clearly see where the moon is intruding over the sun.
That's right. The moon, it looks like a dark piece of coal. I guess in a way we're getting a coal in Newcastle, aren't we? There in Australia, Newcastle, Australia.
I knew that was going to happen.
I couldn't help. It's so late. It's the wee hours of the morning here. We could be excused for these things. Also, the fact that we're just staring at fuzzy clouds right now produces a certain amount of desperation too in our narration.
Well,
but
let me ask Lucie then about something that you brought up to me a little bit earlier. And Lucie, this is a field I know nothing about, and that is helioseismology. Talk to me a little bit about that, about this new study that we're doing of the sun's surface.
Oh, helioseismology is absolutely fascinating, and that's really where a lot of the cutting edge solar research is at the moment as well. But yeah, what is it? Well, helioseismology is the technique where you use the fact that the sun rings like a bell. So this was a discovery in the 1960s in terms of the observations, but the explanation didn't come until a decade after that. So in the 1970s, it was realized that the sun has sound waves trapped inside it, and there are millions of different notes that are ringing around the sun. And okay, we can't hear them directly, but what we can do is see the sound waves, because sound is emotion. And we can pick up the motions that they cause at the surface of the sun. So the photosphere, again, incredibly interesting place, and now is telling us not only about sunspots and the sunspot cycle, but about what's happening deep inside the sun.
But when we talk about seismology here on the Earth, we're talking about the plates that surround our planet as they move against each other or move under each other. But there are no plates on the sun, are there?
No plates on the sun at all. But I think the technique is analogous. So the use of sound waves that propagate through the Earth's interior to tell you about that interior is the same as what we're doing on the sun. The sound waves that go through the sun and that we pick up at the surface carry information with them about what's happening inside the sun. And I think some of the most exciting research has been that showed us the structure inside the sun. What layers are there inside? So we know about the surface and the atmosphere with the photosphere, the chromosphere above, and then the corona at the very extended regions. But what is it inside the sun? And helioseismology has shown us the size of the core, where we've got fusion and the creation of sunlight. It's shown us that inside the sun there is a sort of a subsphere that rotates like a rigid body. But then on top of that is another layer that has a very complex flow pattern, and we call this the convective zone. That sits just underneath the photosphere. And then the other interesting and exciting area of research has shown us the heartbeat of the sun. And it's shown us how these complex flows can actually wind up and evolve the sun's own magnetic field and ultimately lead to the creation of the sunspots and the creation of the sunspot cycle itself. So we would never have been able to answer these questions, or at least work out which theory is right, if we didn't have helioseismology giving us the ability to see inside the sun, sort of put a stethoscope on the sun. So this is really new work that's still coming out.
It's really nice to listen to someone who obviously has a passion about what she studied. It's obvious from the way you speak, Lucie, that this is something that you are incredibly interested in. I thank you so much for spending this time with us from Japan this afternoon. We so appreciate it. Dr. Lucie Green is a solar scientist at the Mullard Space Science Laboratory at the University College in London, and she joins us this afternoon from Japan. Thank you so much for taking the time out of your day to tell us more about the sun.
Oh, it's been an absolute pleasure. I always love to talk about my favorite object.
All right, and we are going to be joined by Dr. Jay Pasakoff in just a couple of minutes. Before we do, if we can really quickly, let me just remind everybody that we're coming to you from Slooh.com. It's a astronomical community that is centered around our Slooh telescopes in the Canary Islands and in Chile. If we have a moment a little bit later, we'll show you some of what our members have been looking at recently. We have been looking at this annular solar eclipse, which is a partial eclipse over the Australian continent, and we will get back to that in just a few minutes. If you'll stay with us, we'll be back with Dr. Jay Pasakoff. So stand by, we'll be right back. And welcome back. We're on Slooh.com. I'm Jeff Fox, and I am joined by Bob Berman, who is our Slooh astronomer. For those who just joining us, we have been following the annular eclipse, which has been an annular eclipse in portions, very small portions, of Antarctica, and a partial eclipse over portions, or actually all, of Australia. And as you can see from the picture we have now, cloudiness has made it impossible to see where the moon is currently blocking the sun in Australia. So we'll keep that feed around just in case things clear up. But while we're waiting for that, Bob Berman, why don't you come back and join me, and let's talk about some of the things that that our Slooh members do, because I know that there are some folks who come and join us just for these special broadcasts, and sort of know that Slooh is a community of astronomy, but don't know exactly what we're talking about or about these telescopes. So maybe this is a good time to show just a little bit of the imagery that our members have gotten in the past week or so. And in fact, let me show you this image that was taken today from our member Hilda Keynes Garduno, and this is the Whirlpool Galaxy. Bob, give me an idea of what we're looking at here on this, and how easy or difficult it is to obtain imagery like this with the Slooh scopes.
Well, with the Slooh scopes, it's easy. You just command the telescope. You just click on Whirlpool Galaxy. The telescope does all the work, the CCDs, the image processing, and there you go. These are two galaxies in a state of near collision. Little galaxy on the top, NGC 5195, is pulling on the main galaxy and pulling off a whole stream of material like pizza cheese, like a long stream of stuff is coming between the two galaxies, and it's just gorgeous. You can see the blue spiral arms of the main galaxy, a beautiful grand design spiral galaxy, and a favorite object here in the constellation Canis Venatici in the spring sky. So it's just gorgeous. About 35 million light years away, by contrast to the eclipse that we were watching until a few minutes ago when clouds covered it up. The moon is only 1.5 seconds away at the speed of light. The Earth is 8.5 minutes away at the speed of light. This galaxy is 35 million years away at the speed of light.
Now, you know, Bob, that I am a meteorologist by training. And when we see two objects like this that are spinning, let's say two hurricanes in close proximity or two low pressure systems, we sometimes talk about the Fujiwara effect, which one actually affects the other. And in essence, they can dance around each other. Can that happen with galaxies as well?
Oh, yeah, they can combine into one, just as Andromeda and our own Milky Way are expected in only some 5 billion years from now to combine into a single football-shaped galaxy that's even been named, called Milkomeda. And this will happen. The only thing is there's an inequality in the masses of these two galaxies. That little one on the top has already passed through the bottom one, has come straight toward us like in 3D. Boom, just broke right through it, and now is above it and is going the other way. But eventually they're going to merge.
All right, let's take another look at another image. This was taken on the 26th, and this was taken by our Slooh member, Craig Edwards. And of course, that is Saturn.
Yes.
Saturn is a target that is looked at often by amateur astronomers.
Yes, and very appropriate, because in only another 10 days from now, Saturn will be at its closest to Earth of the year, biggest and brightest through a telescope. And the fact that this was just recently taken through through the Slooh telescopes, you can tell that it's recently taken, because if we had cheated and showed you an old Saturn image, you would know it. Because look, Jeff, right back from Saturn, you can see a little bit of its shadow being cast on the rings directly behind it.
Right.
And the fact that that shadow goes straight back shows that, if you can visualize this, that Earth, us, looking at it, must be sitting between Saturn and the Sun. The Sun must be over our shoulder and coming straight down towards Saturn in the same direction we're looking at Saturn, for the shadow to go straight back like that. Well, just a month ago, that shadow line went off to the right. That shadow didn't go straight back. It went off a little bit to the side, showing that Earth was not in the same line as the Sun. We were not between the Sun and Saturn wasn't at its nearest. Saturn is only at its nearest when we're between the Sun and Saturn, and that's what's happening this month.
Phases of Saturn as we see the phases of the moon?
Oh, that's an excellent question, Jeff. We can't, because we're 10 times closer to the Sun than Saturn is. And so from our perspective, Saturn is always a full Saturn. So we don't quite get phases. What we do see is a change in the angle of those rings. Now, the rings are more wide open than they have appeared in 6 years. Right now, notice at the very bottom of the planet, you can see just a tiny piece of Saturn, that is the South Pole, protruding below where the rings cross in front of it. And at the top, you can see just a little piece of Saturn blocking the rings. In other words, if they're a little more open than that, you're going to start to see the outer edge of the rings, called the A-ring, extending clear around the planet. And that's the way it's going to look starting next year. What a contrast to just 4 years ago, when the rings were edgewise, perfectly edgewise.
So one of the things that makes this image so cool is the fact that it was taken by one of our Slooh members. When you become a member of Slooh, you can take time on our telescopes and command them to look at you one. And our members look at lots of interesting things. Now, we've shown you two things that are, I hate to say this, Bob, but you'll probably agree with me, sort of pedestrian, easy to see things in the nighttime sky with our Slooh telescopes. But people also track and research near Earth asteroids and comets and supernova. And all sorts of great imagery can be gotten with our telescope. And of course, any member can see any of the imagery that any of our members requests. And when you become a member of Slooh, you also have the ability to have slots where you can actually command the telescope to look at those things that interest you. I guess one of the cooler parts is, Bob, that when there is something interesting going on in the sky, like when a comet is visible or when an asteroid has been spotted, so many of our members want to see this, that these are the images. Even if you don't have a slot to look on a particular night, you'll probably end up seeing what you want to see from the telescope. And right now we have an introductory membership offer. Go to our website and take a look, see what Slooh is all about, see if this is the kind of thing that interests you. And if you are interested, if you do think it excites you, for $29.95, you can join for 3 months, become a member of the Slooh community, which is a very active community of observers of the sky. A lot of these people are folks who, like you, have a passion for astronomy and who want to make sure that those around them learn as much as they can. So if you're starting out, if you have questions, there are people to answer your questions, to guide you in the right way, and some very specific and detailed instructions to help you get your first observations, to help you see what you want to see, and to help get you started. Go to the website, take a look. It's Slooh, SLOOH.com. Bob, I'm afraid we're not going to be able to see any more of this partial eclipse tonight from Australia. It looks like we have fallen victim to terrestrial weather.
We have, but you know what? We got it. We saw the moon and the sun lining up, and incidentally, this is going to cause pretty strong tides. You know, we get when the moon and the sun are in the same line in the sky, we get what are called spring tides that spring up at you. The origin of that term is a little bit obscure. Maybe ancient people thought that it acted like a spring of water coming toward you. But in the next day, today and tomorrow, look for nice high tides that'll wash out more of the beach than usual, and low tides, a good time for clammers, people going out digging for clams because of this lineup of the moon and the sun. And we saw it, we got it. You know, that it clouded up for the later half of it, that's okay, because we really got the essence of it.
And of course, we'll be back broadcasting from Slooh as events occur. Bob and I were talking a little bit earlier. I would not be surprised if we will be around at the end of May. There have been some predictions made, becoming more numerous in the past few days, that the Earth passing through the orbit of the comet, I believe it's
Linear.
209, 209P Linear being named after the actual automated telescope that discovered it. That there is a pretty good chance that we could have a really fine meteor shower, maybe even a meteor storm, coming up on the morning of May 24th. So we'll have more on that as we get a little closer. Bob Berman, thank you so much for joining us this morning, this late night, early morning from New York State. And I am Jeff Fox. I've been here with you from Southern California, and we specifically thank our partners in Australia who have been very generous in allowing us to take their feed, specifically Gerard Lazarus, who has provided us this feed from Newcastle in southeastern Australia. To all of you around the world, thank you for joining us this morning, and have a very good night.